Welcome to our first video. Albert Einstein supposedly called today's topic the eighth wonder of the world, and he had this warning that went along with it. He basically said that those who understand it earn it, and those who don't, well, they pay it.
Which is, a pretty ominous way to look at finance, but
Yeah.
he wasn't wrong.
No, not at all. So today we are doing a deep dive into the invisible and honestly sometimes ruthless math of compound interest. We're going to completely break down the mechanics of how this single mathematical concept builds these monumental fortunes over a lifetime.
Right. And we'll also uncover its surprisingly deep historical roots, which are fascinating.
Yeah, they really are. And crucially, we're going to look at how to avoid the trap of having this exact same force turn against you.
Yeah.
Because you listening right now, this is an essential mission for your financial survival.
It really is. And, whether Einstein actually uttered that famous quote or not is kind of beside the point, right?
Right.
Because the sentiment itself is flawlessly accurate. Compound interest is literally a force of nature in the financial world. The problem is, and this is where people get stuck, that human brain is just fundamentally not wired to comprehend how it actually functions.
Because we think linearly, right?
Exactly. We evolved to think in straight lines. Like, if you walk 10 paces, you are 10 paces away. If you gather 10 berries a day, in 5 days you have 50 berries. We just intuitively expect inputs and outputs to match in this straight, completely predictable line.
And that linear expectation is exactly where people get tripped up the second they hear the word interest. I mean, I know I used to.
Oh, absolutely. Most people do.
A lot of people just assume it all works like a simple, flat payout. Like, okay, you have $100, you earn 10% simple interest every year, which means the bank basically hands you a $10 bill annually.
Right, the simple interest trap.
Yeah, so year 1, you get $10. Year 10, you get $10.
Yeah.
Year 50, $10. The interest you earn is just never added back into the original pool of money. It is completely static.
And that static nature makes simple interest very easy to understand, but it also makes it a terrible vehicle for building long-term wealth. Compound interest, on the other hand, breaks that linear rule entirely.
It just completely shatters it.
It really does. It is, quite simply, interest earning its own interest. Your balance grows, and then the subsequent interest is calculated on that new, larger balance. It shifts from linear growth to exponential growth.
To visualize the mechanics of that shift, let's look at the classic snowball analogy, but we actually need to look at it geometrically to really get it.
I love the geometric angle for this.
Right. So when you start packing a snowball and you roll it over the snow, you aren't just adding a flat amount of weight. Every single time that snowball revolves, its surface area expands.
Yeah, the outside gets bigger.
Exactly. And because the surface area is larger, it physically touches more snow on the ground during its next revolution. So it allows it to pick up geometrically more snow than it did the time before.
The expanding surface area is like the perfect way to look at it. The snowball isn't just getting heavier. Its capacity to accumulate actually accelerates with every rotation.
It's gaining momentum.
Yes. So if we translate that geometry back into your $100 example with a 10% annual return, well, the first year looks identical to simple interest. You earn 10%, so you have $110.
But year 2 is where the math kind of detaches from our linear intuition.
Exactly.
Because you don't earn another flat $10. You earn 10% on your new total of $110, which means your interest is now $11. So your total balance becomes $121.
Right.
And then year 3, you earn 10% of $121, netting you $12.10.
And I want to pause on that extra single dollar you earned in year 2 and that extra $2.10 in year 3.
It seems so small.
It does. It is incredibly easy to just dismiss those amounts. Like, you might not even stop to pick up a stray dollar on the sidewalk. But in the architecture of compounding, that extra dollar is the actual seed of your exponential wealth.
Oh, I like that. The seed, or like the tree analogy, right? You plant a seed, it grows into a tree, that tree drops seeds, and eventually you have an entire forest from just one seed.
That's spot on. You essentially hired a new employee for free. That extra dollar goes to work right alongside your original 100, recruiting fractions of other dollars, which then become whole dollars, which then go out and recruit more.
Which means the most important factor in this equation isn't necessarily the size of the snowball you start with, it's the length of the hill you roll it down.
Yes, time. Time is the ultimate lever here. The longer the timeline, the more cycles of growth your money undergoes.
Because in the actual formula for compound interest, time sits as the exponent, right?
It does. And mathematically speaking, an exponent will almost always overpower a simple multiplier or even a large initial principal, assuming it's given enough runway.
Okay, I want to set up a scenario to really test your intuition on this, listening to this right now. Because seeing the actual numbers play out completely defies logic the first time you encounter it. Let's compare two people, person A and person B.
Okay, let's do it.
So, person A is 20 years old. They decide to save just $100 a month, and they maintain that exact discipline for 40 years until they turn 60.
A very steady early start.
Exactly. Now, person B doesn't start at 20. They wait until they are 50 years old. They feel super behind, so they drop in a $5,000 lump sum to kick things off, and then they aggressively save $500 every single month for 15 years until they also hit 60.
All right, so let's look at their actual out-of-pocket contributions first. Person A steadily contributed a total of roughly $54,000 over 4 decades.
Right.
Person B, trying to make up for lost time, contributed a total of $95,000 out of their own pocket over just 15 years.
Instinctively, looking at those contributions, person B has to end up with more wealth. I mean, they invested almost double the actual cash. They worked harder, they saved a much larger chunk of their paycheck, and they just put way more skin in the game.
It feels like they should win, yeah. But the math doesn't care about perceived effort.
It really doesn't.
Assuming a relatively standard 4% monthly compounded return for both individuals, person A ends up with roughly $151,550.
Wow.
And person B, despite investing almost double the actual cash, ends up with only about $132,147.
Wait, really? Person A beats them by almost 20 grand?
Yes. Person A comes out way ahead, despite giving up like $40,000 less of their own actual income.
That feels almost unfair. Person B sacrificed significantly more of their monthly cash flow, yet they lost. Why does the math punish person B's delay so severely?
Well, it comes down to a concept called doubling cycles. This is the underlying mechanic of that time exponent we talked about.
Okay, how does that work?
When money compounds, it basically operates on a schedule of doubling its value over a certain period. Person A's initial dollars, the ones they invested at age 20, have been sitting in the market long enough to go through 3 or maybe even 4 entire doubling cycles.
Ah, I see.
Yeah, so by the time person B starts at 50, their dollars only have time to go through maybe 1 doubling cycle before they hit age 60.
So person A's original $100 bills from their 20s turned into $200, then $400, then $800. But person B's massive $500 contributions only had time to turn into $1,000 before the clock ran out.
Precisely. The compounding curve is relatively flat for a very long period, and then it turns sharply upward, like almost vertical. Person B stopped their timeline just as their curve was beginning to steepen. They simply ran out of hill.
Which brings up a very practical issue. You mentioned doubling cycles and this idea of a flat curve going vertical. How do we actually track that in everyday life?
What do you mean?
Well, if you look at a savings account or an investment, it's pretty difficult to conceptualize when that money is going to double without, like, breaking out a scientific calculator to run complex exponent equations. And I hate doing complex math in my head.
Most people do. To measure the speed of that growth without doing advanced algebra every single time, you first need to look at the compounding frequency.
Frequencies, okay.
Yeah, the stated interest rate is only half the story. The speed of growth is heavily dictated by how often the institution actually calculates that interest and applies it to your principal balance.
Meaning it doesn't just happen on New Year's Eve every year.
Far from it. Compounding can happen annually, semi-annually, quarterly, monthly, or even daily.
Daily, like every single day.
Every single day. Think about high-yield savings accounts, or CDs. If you have an account that compounds daily, the institution calculates 1/365th of your annual interest rate and adds it to your balance every single night. And then the next day, you are earning interest on yesterday's tiny fraction of interest. Because those microscopic additions are put to work immediately rather than waiting for the end of the year, daily compounding will always result in much faster growth than annual compounding at the exact same interest rate.
That makes perfect mechanical sense. But it still leaves me with the problem of doing math in my head. Is there a shortcut? If I find an investment compounding over time, how do I easily figure out that doubling cycle you mentioned earlier?
Fortunately, finance actually relies on a very elegant mental shortcut for this exact problem. It's called the Rule of 72.
The Rule of 72. Okay, I've heard the term thrown around, but how does it actually function?
It's a remarkably simple formula. You just take the number 72 and divide it by your annual interest rate.
Okay.
The resulting number is the exact amount of years it will take for your money to double.
Really? Let's test that. Say I have an investment generating a 6% annual return.
All right, you divide 72 by 6. The answer is 12. So at a 6% return, your money doubles every 12 years.
Just like that.
Just like that. If you invest $10,000 today, in 12 years it becomes $20,000. 12 years after that, $40,000. 12 years after that, $80,000.
Uh-huh. That is incredibly empowering. I can literally map out a 36-year financial timeline in my head in about 10 seconds.
It completely demystifies it.
Yeah. So if the return is, let's say, 8%, 72 divided by 8 is 9, the money doubles every 9 years, it just strips all the intimidation right out of the exponential formula.
Exactly. It gives you a concrete framework to understand the velocity of your money. But what's truly fascinating to me is that while we use modern shortcuts like the rule of 72 today, the struggle to understand and manage exponential math has been a central theme of human civilization for literally millennia.
Really?
Oh, yeah. This isn't an invention of modern banking.
That makes me wonder how ancient societies dealt with this then. If we aren't naturally wired to understand exponential growth today, how on earth did they handle it before calculators?
They studied it obsessively out of pure necessity. Archaeologists have actually uncovered clay tablets from ancient Babylon, dating roughly between 2000 and 1700 BC, that contain rudimentary algebra problems specifically designed to solve for compound interest.
Wait, 4,000 years ago?
Yes. They were actively figuring out the mathematics of grain and silver loans.
So they fully grasped the concept of the expanding snowball even back then.
They grasped it, and in many subsequent cultures, they became absolutely terrified of it.
Terrified? Why?
Well, under Roman law, and in the legal frameworks of several other ancient and medieval societies, charging compound interest was strictly condemned. It was heavily regulated and often outlawed entirely as the absolute worst kind of usury.
Why the intense fear, though? Did they view the math itself as inherently evil?
They viewed it as a literal threat to societal stability. Think about the underlying mechanics of an ancient agrarian society. The whole economy is based on the physical limits of the earth.
Right, like farming.
Exactly. A field of wheat can only produce so much grain per acre. An ox can only plow so much dirt in a day. The ability of a human being to generate wealth is strictly linear and capped by physical reality.
But the math of compounding has absolutely no physical limit.
Exactly. A debt that compounds exponentially will eventually outpace a farmer's linear ability to grow crops to pay it off. The debt grows faster than the physical world can sustain.
That is wild.
The Romans understood that if compound interest on debt was left unchecked, a small loan could theoretically grow to consume a person's entire lineage, their land, and eventually destabilize the whole regional economy. They saw exponential debt as a mathematical monster.
That is a profound way to look at it. The abstract limitlessness of math just colliding head-on with the hard limits of the physical world. Obviously, the total ban on compound interest didn't last forever, or, we wouldn't be talking about it today.
True. As global trade networks expanded during the Renaissance, financial mechanisms just had to evolve. A major turning point occurred in 1340 when a Florentine merchant named Francesco Balducci Pegalotti published an extensive guide on mercantilism.
Okay, what was in the guide?
This text included some of the very first printed compounding tables. He was calculating interest rates from 1 to 8% for up to 20 years. He essentially formalized the math for a commercial audience.
So he basically printed a master guide for the rule of 72 way before the mental shortcut even existed.
Precisely. And the literature around it only grew from there. In 1613, a mathematician named Richard Witt published a landmark book in London entirely dedicated to compound interest.
Entirely dedicated to it.
Yes. Before Witt, a general mathematics textbook might contain like a single brief chapter on the subject. But Witt democratized the math. He provided over 100 detailed examples of how to calculate compound interest for things like property leases, essentially teaching the public how to navigate the financial realities of their time.
It's amazing how this one mathematical quirk just became a focal point for the brightest minds of history.
Oh, it actually pushed the boundaries of human knowledge in ways that went far beyond just finance. The ultimate historical intersection of money and pure mathematics happened in 1683, and it involved the legendary mathematician Jacob Bernoulli.
Wait, how does a pure mathematician get tangled up in bank loans?
Well, Bernoulli wasn't interested in the loans themselves. He was obsessed with the theoretical limit of compounding frequency. We discussed earlier how daily compounding yields more than annual compounding, right?
Right.
Bernoulli asked a pretty radical question. What if the compounding frequency never stopped?
What do you mean?
What if interest was calculated every hour, every minute, every millisecond? What happens when compounding becomes completely continuous?
Honestly, without understanding the math, I would just assume continuous compounding causes the number to shoot straight up into infinity almost immediately.
And that was the great mystery. Does a finite principal grow infinitely large if the compounding intervals become infinitesimally small? Bernoulli ran the calculations and discovered that, surprisingly, it does not explode into infinity.
It doesn't.
No. As the frequency increases, the total return tapers off and approaches a hard, unbreakable mathematical limit. In the process of trying to solve this bizarre banking hypothetical, Bernoulli accidentally discovered a foundational mathematical constant.
Wait, are you talking about ease?
Yes. The constant E is approximately equal to 2.718.
I want to make sure I'm really following this. You're saying that E is the constant used in modern physics to calculate radioactive decay. The constant used in engineering and probability theory was discovered by a guy trying to figure out the ultimate ceiling of a theoretical savings account.
That is exactly what happened. Bernoulli proved that the mechanism of continuous growth has a structural limit baked into the very fabric of the universe. The architecture of natural growth was hiding inside financial mathematics the whole time.
That is absolutely mind-blowing. It fundamentally changes how I view an investment portfolio. But it also brings us full circle back to that Roman fear of debt,
Right.
and back to Einstein's warning from the beginning of the video.
He who understands it earns it, he who doesn't pays it.
Right. If this math is powerful enough to reveal the foundational constants of the universe, what happens when you are on the wrong side of the equation?
Well, you experience the very dark side of the eighth wonder. When you borrow money at high compounding interest rates, you essentially become that Roman farmer trying to out-yield a mathematical monster.
Bid credit card debt is probably the most common modern version of this trap, isn't it?
Without a doubt. It is the most ruthless application of compound interest in modern consumer society. We are talking about interest rates that frequently exceed 20%. And remember our discussion on compounding frequency.
Yeah, daily versus annual.
Right. Credit cards do not compound annually. The vast majority of them compound daily.
Daily compounding at 20%. Let's really break down how that actually functions for the listeners so they understand the danger.
Okay, so when you carry a balance past the grace period, the credit card issuer calculates your interest charge based on your daily balance. If you owe $1,000, they apply 1/365th of that 20% rate to your $1,000 today.
Okay.
Tomorrow, your balance is slightly higher. The day after that, they calculate the new interest against the new higher balance. Every single day, a tiny, invisible layer of snow is added to your debt snowball.
And if you're only making the minimum payments,
Then the math is intentionally designed to keep you trapped forever. Minimum payments are formulated by the banks to just barely cover the continuously generating interest while shaving practically nothing off the underlying principal.
that's terrifying.
You are perpetually paying for the snowball's new layers of snow, but never melting the snowball itself. It rolls backward, gaining mass, slowly crushing the borrower's monthly cash flow.
But debt isn't the only way compounding works against you, is it?
Huh.
Because there's a quieter, more pervasive force that acts as negative compounding.
Ah, you're referring to inflation.
Yeah?
Yes, inflation is the silent negative compounder of uninvested cash. If inflation averages 3% a year, the purchasing power of the cash sitting in your checking account or under your mattress is shrinking exponentially,
So it's actively disappearing.
basically. In 24 years, if you just follow the rule of 72, the actual purchasing power of your uninvested savings will be cut perfectly in half.
This definitely requires a change in strategy. I look at it as needing a sword and a shield to survive financially. You need compound interest on your investments to act as a shield against the negative compounding of inflation. It defends your purchasing power.
I like that. And if deployed correctly, those same investments act as a sword to build real generational wealth over time.
Exactly.
This happens when you put money into appreciating assets or when you utilize structures that force compounding. For example, dividend reinvestment programs, often called DRPs.
How do those work?
They automatically take the cash dividends paid by a stock and use them to buy more fractions of that exact same stock, which immediately compounds your ownership. Or you can look at zero coupon bonds, which don't pay out annual interest, but instead aggressively compound their internal value until they finally mature.
But to wield that sword effectively, there is a very strict order of operations. You cannot swing the sword if you are actively bleeding from the back. You have to stop the bad snowball before you can grow the good one.
For sure.
Because think about it, if you are thrilled about earning an 8% return in your retirement account, but you are carrying 20% daily compounding credit card debt, the math dictates that you are rapidly losing ground. Exponents don't care about your good intentions. They only care about the numbers. Slaying high-interest debt has to be the absolute first priority.
Order of operations dictates the entire outcome. You must neutralize the daily compounding debt before the annual compounding investments can truly impact your life.
All right, let's distill all of this. The expanding snowball, person A and person B's timelines, the rule of 72, the Babylonian tablets, and the daily credit card trap. Let's put it all into a tangible action plan for the listener right now.
Perfect. The plan relies on 5 specific steps. Step 1 is the most critical. Start today. Time is the absolute ultimate lever.
Don't wait.
Exactly. Do not wait for the perfect moment. Do not wait until you have a massive $5,000 lump sum like person B. Even if you can only spare a few dollars a week, start the timeline. Give your money the runway to experience as many doubling cycles as possible.
Love that. Step 2, be relentlessly consistent. The math relies on the steady addition of principal to keep the surface area of the snowball expanding.
Step 3, do not interrupt the compounding process. This requires intense psychological discipline.
It really does.
If you pull your invested money out early to buy a car or fund a lifestyle upgrade, you break the chain. You essentially reset the time exponent back to 0, and you have to start rolling a brand new snowball from the very top of the hill.
And step 4 is to continually reinvest. When your investments generate dividends or your savings accounts generate interest, do not spend the yield. Put it directly back into the machine. Let your dollars hire those new free employees we talked about and put them to work immediately.
And finally, step 5, avoid the dark side. Avoid high-interest daily compounding debt at all costs. If you are currently trapped in it, prioritize all your resources to break free from that exponential curve before attempting to build the other.
It's a straightforward plan, but executing it requires real patience. It's the daily discipline to just let the invisible math do the heavy lifting in the background.
It requires a deep understanding of our own timeline. And, as we conclude this deep dive, there's one final theoretical complication to consider.
What's that?
Well, we talked about how Jacob Bernoulli proved continuous compounding approaches a mathematical limit, but human wealth accumulation relies on a very different biological limit, our lifespan. Historically, the human compounding curve abruptly stops around 80 or 90 years.
Right. The time exponent is capped by our mortality.
Precisely. But what happens to the math if our biological limits fundamentally change?
What do you mean?
We are currently on the cusp of radical medical advancements in longevity. What if, in the near future, the average human can easily live to be 120 or even 150 years old?
Wow. That gives the time exponent an extra half-century to just run wild.
Imagine giving a compounding investment an extra 50 years of doubling cycles. The curve wouldn't just steepen, it would go so vertical it practically snaps.
It would be astronomical.
If human lifespans extend by 50 or 60 years, how will that entirely reshape global wealth concentration? How will it warp economic inequality between those who started compounding early and those who didn't? And what will the very concept of retirement even look like when your financial timeline stretches across 2 entire centuries?
That is a staggering implication. The relentless math of the eighth wonder of the world eventually colliding with the future of human biology. It's a fascinating, almost science fiction reality to ponder as you look at your own savings and debt today. Thank you for joining us on this deep dive. Start your timeline, respect the math, and we will see you next time.